The next talk is by Zachary Cohn. He's an ML specialist at Gilt, and he's going to talk to us about recommendations in a Flash, how Gilt uses Spark to improve its customer experience.
It's a flash sale site, so every day is a kind of curated, small number selection of products, but changing every day across men's and women's fashion, but then also kind of kids and home goods. And just to give you a sense of the scale of the data, sort of relevant from like, okay, how much data are we processing through Spark, is millions of members, basically hundreds of thousands of unique items per year that we're looking at from thousands of brands, which are sort of the key dimensions that, that show up from a kind of fashion sense. So Spark obviously has a lot of components. We've sort of been playing around with the SQL streaming, but mostly we're going to focus on today, and what I've kind of we've kind of gotten the most out of so far is through the MLlib and really the machine learning tools that Spark has built into it. So I want to kind of step back and say, okay, well, what are we actually trying to personalize? Like, why are we trying to do it for our business use case? So the first thing is this kind of curate. So given that we are showing a very curated experience, this isn't Amazon, we don't have everything every day. We need to find a way to get things that are relevant or interesting, or when we're highlighting sales, things that are just going to be informative. And generally, our need is to have someone find something. So if we want to drive people to come to the site every day, just from a kind of experiential perspective, or we want to encourage that kind of window shopping behavior, we need people, not everything has to be relevant, but something has to show up there. And that's really the core problem we're looking to solve. So the first thing is just kind of recognition, right? And the simplest one of that, not quite visible here, right, is if we know your name, well, it'll show up there, right? When I log in, I see men's products featured. A random person is going to see women's. So that's kind of like the bare bones idea of recognition that we know your name, right? In addition to that is sort of the idea, well, if you've purchased something before, we should tell you that, hey, we remember you did this. We're highlighting this for that reason, right? To be able to reinforce the behavior so people get that experience. But the value add is really to highlight things that we think they're interested in, even though we don't have explicit information about it. And that's really the collaborative filtering machine learning component, is to say, here's something which we have a point of view on based on activity that you have, even though it might not be something that you recognize. And that's sort of how I think about the personalization. There's the kind of explicit form, either things that people have told us or things that we're pushing on them and saying, we're recommending this for you. There's also a lot of implicit recommendations where what actually just shows up on the page when you visit, what's the order of things. Those things are basically recommendations, right? We're making choices on that ranking problem for users, even though we're not necessarily communicating directly like, hey, we think you might want this. So because we have constantly changing inventory, and we need to kind of learn across that. So we're a little bit different in some ways from the kind of traditional item-based recommendations, right? We don't have the same items every day, so we can't say, well, you like apples, you like oranges, because maybe we'll never have oranges again. And the other component is, well, Netflix kind of popularized this idea of, well, the Netflix prize, I should say, right? Popularized idea of you have explicit feedback, rating from people. You sort of need a way to do that without asking, right? People don't actually rate things. And so what are the features that we're learning from if we can't learn from individual SKUs? So we try to learn from categories, right? If you buy a dress, you probably are in the market for dresses. But then also things like the size, price points, right? To what extent are you looking for luxury or premium items? More stylistic choices like color or like A-line dresses, patterns. Each of those things now have to get kind of featureized in a way that we can do collaborative filtering at the feature level as opposed to doing it at the item level. And of course, brand. So item-based is definitely the most popular. That's also because it has a lot of computational advantages. And that's what's kind of built into Spark and what we're using Spark for here. People kind of expect this, and even the obvious stuff where you really just say, oh, you like dresses, so here's another dress, obviously has a lot of value. The better you get at it, the more value you can extract. But even the things that seem like, oh, this is pretty natural, is worth doing, right? So if you like one bespoke Italian suit manufacturer, maybe you like another, our ability to make those inferences without having to have someone go in from our merchandise department and say, this is like a small Italian suit manufacturer, you should make this connection, right? That's where a lot of value comes from, because at scale, as we have hundreds of thousands of products, we're not going to have the manpower to be able to manually curate all these things. So this is sort of our personalization stack, pretty common kind of Lambda architecture. Data comes in, goes through event streams. Some of that gets logged to data warehouses for batching. Some of that goes through real-time compute. And where we are right now is, in terms of Spark, is really using that as part of the back processing. Definitely, we're kind of looking at understanding how we can hook that up to what we're using for event streams. But in a lot of ways, batch is an easy place to start to kind of prove out the concept. We don't have to necessarily worry about the productionization, because we can spin up a cluster, do what we want, take it down, see if it works, and then iterate from there. So for those of you who are kind of Python developers, right, this title is for you. This kind of Zen of Python, right? This beautiful is better than ugly, explicit is better than implicit, but no one gives explicit feedback, right? This is the, in a lot of ways, the kind of academic directions for a while were focused around the Netflix prize and the attention that got, and the actually amazing data that was then available in terms of rating movies. But even for the movie space, if you don't like a movie, you still went and watched it. So probably you thought you would like it. So you actually get a lot of information there. And the collaborative filtering, that implicit collaborative filtering in Spark is kind of what we're using, because we don't have people rate items necessarily. But we can see, are they looking at these? Are they buying it? Are they waitlisting it? Right? Those activities are almost as informative as we actually were able to get people to give that kind of explicit feedback. So one nice thing about kind of Spark and obviously the RDDs is it's just very easy to take this from whatever data source we have, right? Mostly we're just dumping this stuff into S3 using Amazon EC2 to load, to take whatever data we want to have in CSV format, load it into RDDs. Kind of doesn't really take much effort. When we actually get to then training the models, right, this is the train implicit method that Spark exposes for in MLlib for learning from these explicit feedback data. There are a lot of kind of model hyperparameters that need to be assigned, right? So one is kind of the rank of the model, sort of latent features, basically giving you an idea of the model complexity. Second is just how many iterations for this matrix approximation that you're doing, basically giving you how close do you want to converge to what is the kind of exact numerical solution. Then the other parameters is lambda, which is giving a conditioning value, and alpha, which sort of is for implicit feedback, saying how confident are you that this implicit signal that you've been detecting, let's say you count how many times someone looked at something, how much activity is required before you believe, right? It's a way of dampening the implicit signal to kind of convert it to something a little bit more explicit. And then, of course, the content, right? So you need to actually load this data in at the start. In the MLlib language is ratings, but it doesn't have to be ratings. So our ratings now consist of things like purchases, views, clicks, that we can then weight separately within the model. So how do we assign these? Well, the first thing is that you should be trying to optimize something, right? So hopefully there's a KPI, some kind of performance indicator that you're trying to do, whether that's revenue per user, although how you do that in a statistically meaningful way is itself an interesting and separate talk, or like likelihood to respond to emails. Some way of saying, well, we have this model that predicts what people are supposed to do. Is it useful? And behaviors can always be A/B tested, right? If we actually have something we want to compare against some static ordering or an existing model, once you have it live, that's kind of the proof is in the pudding. Are you actually making more money from this approach than another? But it is useful to have something for offline model testing. When I'm trying to fit those parameters, I want to say, well, I'll just throw 100 parameters into production, kind of get back to you in a month and figure out which ones make sense. For our problem, it's really precision problem. Getting back to the point, we want people to see something interesting, but whether everything on the page is, everything on the page should be important, but what they don't know what they're missing, right? Like if something that is relevant to them doesn't show up there, that's kind of very soft. It's a penalty, right, that we pay as a business. That way it's a missed opportunity. But it's not something that the customer says, why am I looking at this? Which is really the danger in general of kind of machine learning-based solutions, where when humans make mistakes, they make subtle mistakes, right? When machines make mistakes, they have the opportunity to make kind of big mistakes that people find unintuitive. And that display between what computers think is an intuitive error and what a person thinks is an intuitive error kind of plays a lot into how collaborative filtering-based solutions get judged. So what you have to do in order to then fit these hyperparameters, right, is kind of cross-validate the models. So what I mean by that is you don't want to use the same kind of training data to fit all the parameters as you use to evaluate the model, right? This will overfit the model kind of in the kind of classical statistical sense. And even very kind of elementary separation of training and validation data sets will kind of solve this problem for you. A lot now with the kind of SparkML pipelines makes this kind of a lot easier. But even kind of before 1.3 is out, having just kind of a for loop that you're going around to take care of, take care of fitting these parameters is going to work. You also then need this function. OK, I'm cross-validating to optimize some target. What is that target? And what we're using is sort of the predicted ratings, just the average for rating of things that we assign, average predicted rating of purchases, versus the average predicted ratings for everything else. So essentially, how can we test whether what we're doing is right in an offline environment? Hold something out, see whether we're anticipating that the things that we think people like are things they actually buy versus not. And we can do some cleanup to remove scores that are below a threshold. If we're never going to show this to a user, it doesn't really matter if we're really good at knowing they hate it. And this is essentially borrowed from this pseudo R squared for logistic regression, which is essentially a similar kind of prediction space. And the final thing to keep in mind is when you're doing this kind of evaluation, you don't need to evaluate this on a very large data set, right? Statistics is your friend. You can sample things, figure out how much data you need to sample to get a reasonably good estimate. And this is where you're going to see huge speed ups in terms of how long it takes for you to actually fit parameters with cross-validation. So what does the basic workflow then look for when we're thinking about this training? So we have the training set that we just kind of dump into S3 or anywhere, right? Actually, we're going to separate out some test data that we hold out forever to get a sense of how well we think the model is performing. Then this goes into the cross-validation process I was just describing, kind of building models, validating against these different parameters. And then finally, once that process is done, we have the model we think is best to do it against the holdout set so we have a sense of how well we think things are going to perform. In our case, we actually also have two kind of test sets because we want to make sure that we're not penalizing things that are time-based, right? Because our inventory is changing, we want to understand, well, if we built the model today, use it tomorrow, what's the penalty that we're going to be paying? So model building is fast. So the matrix algebra here is great. Spark makes this very easy. So that's kind of the easy part. Cross-validation is the slow part. So actually kind of figuring out what parameters make sense the first time is really where most of the computational effort goes because you're kind of rescoring all these things. And there are two reasons that kind of plays in. One, if you're doing a grid search across 4 parameters, and maybe you want to try a bunch of different values for each of them, that is going to grow pretty quickly. And also scoring the model for everyone, if you're trying to kind of validate the model, is a huge task to multiply these huge matrices together. So SparkML, which kind of wasn't really in the 1.3 release, now makes some of these things a little bit easier. So you're not necessarily needing to build your own kind of custom code to do the cross-validation and model building pipelining. And you don't really need to do grid search. You probably have some idea of which parameters are more important. There aren't really 4 parameters. Like the rank parameters themselves is maybe the most important one. The iteration and conditioning ones, well, once you're close enough to the answer, you can stop trying to make your matrix more and more exact. You don't really get any value for it. And as I said before, just don't score the universe. You don't really get any advantage from there. So there's this great quote from Confucius on wisdom. Right? It says there are 3 ways you can acquire wisdom. One is by reflection, second is by imitation, and the third is by experience, which is bitterest. So I want to share at the end a couple of experiences that kind of I had with Spark, which maybe would inform how I would tell someone starting out, like, OK, these are the things maybe that don't work. And maybe they just didn't work for me, in which case you should tell me what I'm doing wrong. So this is a persistence of memory, which is always a big question in Spark. How much of the data to keep in memory versus how much to recompute. So the first is that one of the nice things about not relying on in-memory is that it allows you to keep the workflow locally in dev and then in production very similar. So if you're never relying on having a high memory availability, then on a sample of data, you can run basically the exact same code as you'd be running on a larger amount of data, just with more nodes. And to the extent that you're doing an iterative development, avoiding like whatever random things happen only in a development process is always nice. And based on that, like default memory only might not make sense. So spilling to disk, depending might be the best. And sometimes it's better just to not bother caching at all. Right? Some things are fast enough to recalculate that it's easier to recalculate them than to kind of try to recover them from disk. The second one is broadcast variables, which is another kind of use of memory. Even for relatively small data sets like rekeying, you have offline brands with name, you need to assign them IDs to learn from. Even that data seemed like there was a kind of possible point of failure by trying to broadcast memory. Even for relatively small sizes, sometimes the cluster would be unhappy about that. And I would say pair RDD functions now, of course, the data frames and Spark SQL probably are even a better solution here. So I'm happy to take questions if I have any time. The kind of Gilt blog and GitHub pages are there. And I'm Zachary. Thank you.
All right, time for 2 questions. Anyone out there? Here we go. There's one.
Just out of curiosity, on those factors that you put into your model, how do you take seasonality into consideration?
Yeah, so I'd say there are kind of 2 components. One is just the inventory that's available is itself seasonal. So there's some seasonality built into just what's kind of available to sell on the site because we do have rotating inventory. The second is there's kind of a lot of these things I'll say things that are outside, I guess, of the core collaborative filtering model, which we use to understand seasonality just by kind of weighting variables as they come in. So knowing that something that happened 12 to 15 months ago might be more informative than something that happened 9 to 12 months ago, even though the things that just happened are probably the most relevant. So although that I guess I would say it's not built into the implicit training that's in Spark, so it's something that we essentially find a way to enhance it.
Any other questions? All right. Thank you, Zachary.
Thank you.